Hello, welcome to this revision lesson on the data handling module for year 10 scheme 1. Okay, so let's jump right in. So first topic is scatter graphs. Okay, so if you haven't tried this question yet, pause the video and have a quick go of it. Okay, best of luck. Okay, so just a reminder, so just reading the question out first of all. So the scatter diagram shows the price and age of each of 12 scooters of the same make and model. We can see a diagram here. We can see the x-axis tells us how old the scooters are, and the y-axis tells us the price of the scooter. And then we've got 5 questions. Let's work through these one at a time. So A, write down the price of the oldest scooter. Well, the oldest scooter will be the one with the highest number of years. It is the most number of years old, okay? If I look at the highest number of years, I can see you got this value here. Because it's the furthest one right, I take it down to the x-axis. I can see that it is indeed the oldest one, but we want the price. So let's take it over here. And we get, so we're one square above 100, and there's 5 squares between 100 and 200, so that means each square is worth 20. So we have found that the oldest scooter is worth £120. Okay, job done. Let's have a look at the next question now. Write down the price of the newest scooter. Okay, so the newest is basically the new scooter. So we're looking for the scooter that is, if it's new, it's 0 years old. And actually, it's a little bit hidden, but it's actually on the diagram up there. Okay. Now we don't need to draw a line going left to meet the y-axis because, hey, it's already on the y-axis already. We can see that it is 3 cubes above 600. Each cube is 20. So we know it's £60 above 600. So the price of the new scooter will be £660. Okay, so next one. Write down the type of correlation shown by the scatter diagram. Okay, so let's talk about this with regards to x and y. Okay, so as x increases, y, what does y do? So as we go up our x-axis, or our values for x increase, what happens to our y values? We can actually see they're going down. So as x increases, y decreases. And you should all recognize that means that we are looking at a negative correlation. Negative correlation, okay? So, and then this line of best fit now for the next question, that should hopefully prove our answer. So draw by eye a line of best fit on your scatter diagram. So when you're drawing a line of best fit, obviously you want to be using a ruler, but you're trying to get as many points, you're trying to get the same number of points either side of the line of best fit. So that's my go. Quick stab in the dark. I will do better than that. Let's try this. Is hard. It's tricky to draw on a ruler on a computer screen. It's still not quite right. So this is the thing. So obviously you take time with this. You use a ruler. That looks better. Looks slightly better. Oh well, it'll do. So drawn a line of best fit, and again we can see a negative correlation because the line is sloping down to right. That means we have got a negative correlation. Okay. So the next question now is asking, estimate the price of a 2.5-year-old scooter of the same make and model. So now what we've basically drawn here is a conversion graph. We can now use this conversion graph to answer this question. So first of all, let's find the 2.5-year age on the x-axis, 2.5 years old. Each square represents 0.1 of a year. So 1, 2, 3, 4, 5. So that's my 2.5 years old line. And then I'll draw a line straight up until I hit the conversion line, just like that. And then we take that again. You'd use a ruler for all of this. You wouldn't dare do this by freehand because you will get wobbly lines like I have here. Now again, we can see we're somewhere between the two lines. We're somewhere between 300 and 1 cube down. So we're going to take that as half. Each cube is worth 20. So we're looking for 300 take away 10, which would be 290. Okay. How would you make your line of best fit more accurate? More data points. Simple as, okay? So the more data points you have, the easier it is to draw a better line of best fit, because you're able to align your line of best fit so that it matches up with most of the points. Okay, when you've only got a few, it's hard to draw a line that match the most of them, because it's quite easy for a few points to be spread out, whereas as you get more points on there, it's easy to see a clear pattern forming. Okay, let's have a look at the next question. Cumulative frequency. So again, if you haven't tried this question, pause the video and have a quick go of it on your own. Okay, best of luck. Okay, so 140 girls were asked how long they spent revising for their GCSE exams. The cumulative frequency diagram shows the results. Now, these cumulative frequency diagrams, they can be quite confusing. Just to give you a very brief recap on them, what these lines mean, if we start at the bottom here, the fact that the line goes to the bottom, that shows us that hopefully 0 girls revised for 0 hours. So hopefully everyone did some revision. If we then take ourselves to this point up here, this tells us that if we take it across to the y-axis, because that's on the number 10, and so it's 10 on the y-axis, which is the cumulative frequency, and it matches up with 10 on the x-axis, which is the hours revised. That tells me that 10 people have revised somewhere between 0 and 10 hours. Okay, so between 0 and 10 hours, 10 people have revised between 0 and 10 hours. I can't tell you how long any one person exactly revised for, but that's how long they revised for. At least 10 people, 10 people revised between 0 and 10 hours. If we then look at this point here, and we match it up with the x and y axis, so we bring it down, that comes to 50 hours, and we take it across to 60. What this tells us is that 60 people did not revise more than 50 hours, but that 60 people revised somewhere between 0 and 50 hours. Okay, and we can go further with this. We can see that if we look between, if we consider between 60 and 10, so we're focusing on this part of the cumulative frequency diagram there. How many people are represented between 60 and 10? Well, it's going to be 50 people, isn't it? There's 50 people between 60 and 10. And we can now see that 50 people revised between 10 hours and 50 hours. Okay, so they're quite tricky to get your head around, but so it's only a very brief introduction to it. If you want a bit more of a thorough recap, have a look at another one of our live lessons. Okay, but that's just a quick recap on cumulative frequency. So we've got 3 questions here. Estimate the median time the girls spent revising. So what we're trying to find is our middle value. The median time, the middle value. Okay, so if there's 140 girls, what's the middle value of 140? Well, we just do 140 divided by 2 equals 70. So we're trying to find how long the 70th girl revised for. 70th person or girl. She revised for roughly, because this isn't going to be exact, it's going to be an estimate. So we find 70 on our diagram. Again, use a ruler. Don't do this freehand. And take it across until you hit your cumulative frequency line. And then you take that down. So you hit the x-axis. So I can see that I'm going to estimate that the 70th person revised for roughly 52 hours. And this is my median value. And it's only an estimate at the median value because, like I said, we can't actually give we can't give the amount of time any one person revised for. We're only adding up how many people revised certain amounts of times. Okay. Next question. Calculate the interquartile range of the time spent revising. So the interquartile range is equal to the upper quartile, take away the lower quartile. Okay, well, what is the upper and lower quartile? Well, the upper quartile represents the 75% line of the data, and the lower quartile represents the 25% line of the data, if you will. And if we've got 140 people, if we want to find what person represents the 75% position, we need to find 75% of 140. And to find the 25% line of this, we need to find 25% of 140. 140. You can use a calculator, you can figure that yourself, it's just 3/4. So 75% of 140 is 105. Oops, I'm going to draw it a little bit smaller. It's 105. And the 25% of 140 is 35. Okay. Now, these numbers, these aren't how many hours they're revised for. This is the person we need to be looking at. Okay, so we need to find the 105th person, and we need to find the 35th person. Okay, and then we're going to take away their times we estimate they revised for, and that will give us our interquartile range. So let's do that now. So let's find the 105th person. Every cube is worth 2 on this diagram, so we need to go 2.5 up there. So that's the 105th person. Now we're going to estimate their score. Ooh, keep it straight. Estimate their score. Get on the line, and bring that line down so it matches on the x-axis. Bit of a wobble. Cool. So I'm reading that, and I can see every square is worth 1. So that looks to me like it's 58.5 hours. Okay, and I'm going to subtract from that however many hours I estimate the 35th person revised for. So every square is worth 2, so 2, 4, 6, 8, 10. So that's 30, and that will be 30. The 35th person. Take that line across. Take your time. And there, bring it down. Ooh. And then we see that every square is 1 on the x-axis, so we've got 32.5 hours. And if you take those away from each other, 58.5, take away 32.5, you should get 26 hours, and that is the interquartile range. Okay, so that's that one done. A little bit trickier. Again, you need to make sure you understand what this diagram is showing you before you can jump into these questions. But once it clicks, it should be okay. Last question. How many girls spent more than 50 hours revising? So to do this, let's actually work backwards. Okay, so let's find 50 hours on our cumulative frequency diagrams. We've got 50 hours on the bottom here. Let's draw a line up until we meet our line. There it is. Now, let's see how many people will be revising less than 50 hours, because that's what we do. If we take this line to the y-axis now, this will tell us how many people have revised for less than 60 hours. Take it across. Thankfully, it's quite a nice and round 60. So I know that 60 people revised less than 60 hours. Okay, I can see that because you can see the cumulative frequency diagram says that 60 people, this amount of people revised less than 50 hours. And because it says 60 on the x-axis, that's how many people revised less than 60 hours, I should say. Therefore, if we know that there are 140 people in total, if 60 people revised less than 60 hours, that must mean the rest revised more than 60 hours, 50 hours, sorry, I should say. That means the rest of them revised more than 50 hours. Therefore, 80 people revised more than 50 hours. Okay? Because it's just everyone else. If we know 60 people revised less than 50 hours, then the rest of them have to have revised more than 50 hours. Okay, so 80 people revised more than 50 hours. Okay, job done. Good job if you got those right. Let's have a look at the next topic now. So let's have a look at question A. Which place had the higher average rainfall? Now, there's no one bit of information on this that will give you the explicit answer to this question. Instead, we need to look at the whole picture for both. We need to compare and contrast the two. Okay, so just to remind yourselves, these here these two lines that make the whiskers, so to speak, this one is the minimum value and this is the maximum value. And together they represent the range, obviously, because range is the maximum, take away the minimum. This line here is the lower quartile, which represents the 25th percent value, if you will, or just it represents the value at a quarter of the data. And this one represents the upper quartile, which represents the 75% point of the data. And this line here, this gap here, or this distance here, is the interquartile range, which is calculated by the upper quartile taking away the lower quartile. Okay, so, and then this line in the middle here, we have that as our median. Okay, so remember, there's no one point on this diagram that will give us the answer to what which is the highest average overall. Okay, so we need to sort of take everything into account. Okay, so let's compare and contrast the two. So I'm going to talk about, let's talk about a few things. So let's talk about the upper quartile, talk about the lower quartile, let's talk about the interquartile range, and let's talk about the median. And talk about range. Fine, let's talk about all of them. So we're just going to say very quickly which is the biggest, which of the towns, Trevor and Narrabee, have the highest or the most significant feature that would indicate they have a higher average. Okay, so if we compare the upper quartiles, they are the same. They actually have the same upper quartile. Okay, they've both an upper quartile of roughly 45. Okay. Then the lower quartile, well, you can quite easily see here, because I've lined them up, that Trevwen has the higher lower quartile. So Trevwen is higher, which would mean it has which would indicate it is a higher average. Okay. And then interquartile. So which one has the smallest interquartile range? We can see, or which is the smallest interquartile range. So that means the data is a bit more compact. Okay, so actually we can see here the smallest interquartile range is Trevwen again. So Trevwen is the smallest, and that means the data is closer together. Therefore, the average is likely to be in the middle of that IQR. Then, okay. The median, which is the higher median, well, you can clearly see that Trevwen is the higher median as well. Trevwen is higher, and the range, well, we can see that it's a little bit tricky to spot at the start, but the range for Narrabee would be 50 take away 1, so that's 49. So let's write equals 49, and the range for Trevwen, let's just quickly figure this out. So 51, 2, 3, 4, 5, 55 take away 1, 2, 3, 4, 5. 55 take away 5 is 50. So Trevwen does have a higher range, and we would like a smaller range because that'd be slightly more indicative. So range, so technically Narrabee wins that one. So Narrabee has a smaller range. Okay, but if we look at all of this overall, actually, I think it's quite clear to see now that Trevwen has the highest average because it has a higher lower quartile, it's got a smaller interquartile range, and the median is higher. They both share the same upper quartile range. So overall, I think it's fair to say that Trevwen has the higher average. Okay, that's just looking at the whole data. Okay. Next question: calculate the range of the daily rainfall in Narrabee. Well, we've already done that. Look at that. Hey, we calculated to be 49. And the way we did that, the max value was 50, the minimum value was 1. 50 take away 1 is 49 millimeters. Job done. The next question is to calculate the interquartile range of daily rainfall in Trevwen. So remember, interquartile range is the upper quartile, take away the lower quartile. So let's get rid of these and let's find out what those numbers are. So the upper quartile is 41, 2, 3, 4, 5. I'm doing that to be 45. Upper quartile is 45 millimeters of rain, and the lower quartile is a nice and easy 20. So 45, take away 20 millimeters, and that is equal to 25 millimeters, and that is the interquartile range. Okay, so box and whisker plots, again, this is just a brief summary. Feel free to go back to a lesson to double check your knowledge on this topic. All right, let's have a look at the next one. Relative frequency. If you haven't tried this question yet, pause the video, have a quick go. If you've already done it, let's jump right in. So Mr. Tenby is testing a brand new six-sided dice he's bought. He thinks it might be biased, so he carries out an experiment. Remember, biased is another word for unfair, meaning that it's not equal. The chance of getting everything isn't equal. He recorded the number of threes he threw in every 10 throws of the dice. Ooh, threes he threw. Threes he threw every 10 throws. So this is a table. He threw the dice 10 every time. He recorded it 10 times, and he counted the number of threes he got. He decided to create a table to show the cumulative number of the threes thrown, and he used this to calculate the relative frequency. Now, relative frequency is the real life frequency. It's a real life expectancy that you're going to get something, and then experimental frequency is what you would expect. If you think it's a fair dice, and you know there's a 1 in 6 chance of getting a 3, that'd be your experimental frequency. But if you actually test it out in the real world, you would get your relative frequency. And so we can see his number of throws are increasing because it's cumulative. The number of threes he gets is increasing because we're adding up all the number of threes. And the relative frequency, it's not necessarily increasing or decreasing because it's the number of threes thrown divided by the number of throws above each relative frequency. So we do 2 divided by 10, 5 divided by 20, so on and so forth. Okay, so first question, we need to complete the table. So first, we're given the cumulative number of throws, so he keeps adding 10 every time. So let's add how many threes he got. So on his 70 to 80 throws, he got an extra 2. So 20 plus 2 is 22. On the next 10 throws, he got an extra 2, so 24. On his next 10 throws, he got an extra 1, so 25. Now, let's turn these into relative frequencies. Now, we're not going to simplify these for now. We're just going to keep it as a normal fraction. We're not going to simplify it. So he got 22 out of every 80 throws. So simply, we're going to 22 over 80. We could simplify this. We're just going to leave it for now, okay? The next one, he had 24 threes out of 90. So 24 out of 90. And then the next one, he had 25 out of 100. Now, you're going to solve these as decimals, okay? So you're going to get your calculators and you're going to solve these fractions, okay? So 22 divided by 80 should be equal to 0.25, sorry, 0.275. And then the next one, you've got 24 divided by 90. That is 0.26 recurring. So 25 over 100 is 0.25. So, complete the table, job done. Using the above results, write down the best estimate for the probability of obtaining a 3 on Mr. Tenby's dice. Well, we can see if we start at the far left end, we can see it starts off as 0.2. So it looks like there's a 1 in 5 chance he gets it. But as we increase the number of throws, remember the more times you throw the dice, or you roll the coin, or you roll a dice, throw a coin, anything, that's going to get you closer to your true relative frequency. So actually, we can see this number, it bounces above and below 0.25, but eventually, once we've thrown it 100 times, we stop bang on at 0.25, which is the same as a quarter. So I would say the probability of obtaining a 3 on his dice is a quarter. And the reason we can give a reason for this is the relative frequency. Relative frequency moved as barely deviates, or barely. The relative frequency doesn't change much from 0.25 after 100 throws. Okay, so it's basically saying that after 100 throws, our relative frequency is hovering around that 0.25. It's not running away from it. It's not getting too low from it. It's settling at about 0.25. Okay. Is the dice fair? Explain your answer. That's going to be a big fat no. And the reason is it should be 1 in 6 relative frequency. Should be a 1 in 6 chance, or 0.16 recurring if it was fair. So the relative frequency should be 1 over 6 or 0.16 if it was a fair dice, because there's only one number 4 on a 6-sided dice. Okay, next question. After continuing this experiment for a very long time, Mr. Tenby had thrown the dice 4,400 times. Crikey. He calculated the relative frequency of getting a 3 as 0.15. How many 3s did he roll in total? Well, if he rolled a dice 4,440 times and he worked out the relative frequency to be 0.15, all we need to do is multiply the number of times he rolled the dice by his relative frequency, and that will tell you how many times he got that dice, and we can reverse engineer that in a bit. So very quickly, if we do 4,400 multiplied by 0.15, type on your calculator, you should get 660 threes. Okay, and just to show you how we can reverse engineer this, just to double check it for yourself. So that's our final answer, 660. But let's pretend we knew he rolled 660 dice out of 4,400 times. So 660 out of 4,400. That's the same as writing 660 over 4,400. And if you press equals on the calculator, you will get a relative frequency of 0.15. So that's just showing you how it works both ways. Okay, but he got 663s. So well done if you got that. Okay, let's have a look at the next question now. Probability trees. Again, if you haven't tried this question yet, pause the video, have a quick go. And if you have already done it, let's jump right in. Karis has a Monday to Friday job and a weekend job. Working Monday to Friday and working weekends are independent events. That just means that one doesn't affect the other. In any given week, the probability that Karis works every day from Monday to Friday is 0.65. The probability that she works both days during a weekend is 0.2. We've got our probability tree here. So question A, complete the tree diagram. Well, both of these, so for each tree, for each starting branch of the trees, these two numbers have to add up to equal 1. Okay, so all of these numbers have to equal 1. These two numbers have to equal 1, and these numbers have to equal 1. Okay, so something plus 0.65 is 1. That's going to be 0.35. Again, looking at this part now, something plus 0.2 is 1. Well, that's going to be 0.8. Now, the key word, because these are independent events, that means the chance of her working on a weekend is unaffected by her working in the week. So these branches should be exactly the same as the branches above them. So we can put in 0.2 and we could put in 0.8. Okay, so that's question A done. Part B now. Calculate the probability that next week Karis will only work from Monday to Friday. So start on the far left of the tree. She's only working Monday to Friday. So does she work Monday to Friday? Yes, she does. So we've got this branch. So we're here now. Now she's only working Monday to Friday. So that means she isn't working on the weekend. So we're going to go on the no branch, on the weekend probability tree. Now, remember, when we go from left to right on the probability trees, that means we multiply the probabilities. Okay. And then if we're trying to find lots of different outcomes, so she works weekend and week, or she doesn't work the week. Then when we go down, we add the final outcomes up together. Okay. But for now, we're only looking at only working in the week. So yes to work in the week and no to working on the weekend. So what is the probability of this? Well, the first value is 0.65. 0.65. I'm going to multiply that by 0.8 because she doesn't work on the weekend. So 0.65 times 0.8. And that is going to be equal to 0.52. Job done. There's a 0.52 chance that she will only work Monday to Friday. Nearly, very close to 50-50. Slightly more chance that she does do that. And then part C now. Calculate the probability that next week Karis will not work all 7 days. So let's think about this. So we're saying she doesn't work all 7 days. So does she work Monday to Friday? No. Does she work on the weekend? No. Again, remember, we're going across the tree, so we're going to be multiplying, okay? No, so therefore we're going to do 0.35 multiplied by 0.8. Type that in your calculator, and you should get 0.28. So nearly a quarter chance that she will not work any days at all. Not very good for her income, but hey, that's how it rolls. Okay. So well done if you got those 3 right. Let's have a look at the next question now. So probability trees, but without the trees. So if you haven't tried this question yet, pause the video, have a quick go. And if you have tried it, let's jump right in. Shanaz has a bag containing 6 pens. 3 pens are red, 2 are blue, and 1 is green. She takes pens out of the bag at random and without replacing them. So that means she doesn't put them back. Okay, key part of the question there. Calculate the probability that the first 2 pens she takes out are the same color. So there's 3 different color pens, okay? So let's consider the following probabilities. So she gets red and red, or I'm going to add that. She gets blue and blue, or she gets green and green. Now, some of you are probably screaming at me through the screen saying, but sir, there's only 1 green pen. There's no way she can get out 2. And you're absolutely right. But I am just going to keep this in just to show you that it works, even if you're having a bit of an off day. As long as you do the maths right, you will still get the same answer. Okay, so let's run through this. So probability, she gets first 2 pens the same color. So what's the chance she gets a red pen, then a red pen? Well, 3 of the pens in a bag of 6 are red. So first of all, we need to do 3 over 6 times. So the first chance is 3 out of 6. Now we've taken out a red pen and we've taken out a pen out of the bag. So not only is there 1 less red pen, there's also 1 less pen in the bag in general. Multiply these fractions together. 3 times 2 is 6. 6 times 5 is 30. Happy days. Now we're going to leave this. We're going to leave that as over 30. You'll see why later. Hopefully you might remember why. Now, what is the probability of getting 2 blue pens? Well, the probability of getting the first blue pen, there's only 2 in a bag of 6, so it's going to be 2 over 6. And we're going to multiply. Now there's 1 less blue pen, so there's 1 blue pen left, and there's 1 less pen in the bag, so 1 over 5. Multiply these fractions together. 2 times 1 is 2. 6 times 5 is 30. I'll leave that in there. Leave it as 30. Now, P over green. Some of you, like I said, some of you might have said there is only 1 green pen. Well, you'll see now that even if you do the maths, you'll still get the same answer, and you could be nice and thorough. But that's what we should prove to you why it's impossible. Even though we know it's impossible, we can prove it's impossible with maths. So, what is the chance of her getting a green pen out of the bag the first time? Well, there's only 1 green pen in there out of a bag of 6, so 1 over 6. Now, how many green pens are left? There's none. And how many pens are left in the bag? Well, there's 5. So that's the chance of getting 2 green pens, 1 over 6 and 0 over 5. If you multiply them together, 1 times 0 is 0. 6 times 5 is 30. And remember, 0 over 30 is the same as 0. 0 divided by anything is just 0. And as a probability, 0 means it's impossible. So if you spotted that and you didn't even think about the greens, very well done. But this is hopefully proving to you that even if you did include it, as long as you did the maths right, it should all pan out still fine, okay? So here we go. We need to add up, because these are all red, red, or blue, blue, or green, green. We now need to add up these outcomes. Because they're all over 30, they should be nice and easy. 6 plus 2, 8 over 30. And if you turn that into a decimal, you should get 0.26 recurring. Okay, so very well done if you got that right. Now let's look at part B now. So calculate the probability that of the first 2 pens she collects, at least one of them is blue. Now, there's a really, really long way to do this, and there's a really, really easy way to do this. The really, really long way, now I'm going to draw a probability tree just to highlight this. You wouldn't draw this in the exam. Well, tell you what, you could if you really wanted to. It would just take a while as well. But if you can recognize this just by reading the question, that's what we're after. So, of the first 2 pens she selects, at least one of them is blue. So the options for this probability tree are going to be blue and not blue. So B prime. Okay. In each branch, she either gets a blue pen or she doesn't get a blue pen or not blue pen. Now, what are the final outcomes here? Well, we've got probability of blue, blue. We've got probability of blue and not blue. We've got probability of not blue and then blue. And we've got probability of not blue twice. Okay, so which of these outcomes does she get at least one blue? So she has at least one blue pen. Well, it's this one, it's this one, and it's this one. Okay, so if you wanted to, you could calculate all 3 of these outcomes, and if you added them all up, because it's blue and blue, or blue not blue, or not blue blue, if you added them all up, you would indeed find the probability of her selecting at least one blue pen. However, remember all of these outcomes, so there's only 4 different outcomes, and all 4 of them have to add up to 1. So actually, if we calculated the chance that she doesn't get any blue pens, and we took this away from 1, we would get the sum of the other 3 outcomes. Okay, so what we're going to find is 1 take away the probability of blue prime, which means she doesn't get any pens. So let's do that. So 1 take away blue prime, blue prime. What is the chance of her not getting a blue pen? Well, there's 4 non-blue pens in the bag to start with, so 4 over 6. And then if the second time, there's going to be 1 less non-blue pen, but there's also going to be 1 less pen in the bag in general, so 3 over 5. And then multiplying them together, 4 times 3 is 12, 6 times 5 is 8. Oh, that's not right at all. 6 times 5 is 30. Got 8 on the mind there. 1 take away 12 over 30. Well, that's the same as 30 over 30. Take away 12 over 30, so you'd be left with 18 over 30. And as a decimal, that would be 0.6. So there you have it. There was either a really long way to do it, or there's a really easy way to do it, but it's not. So whilst you didn't need to draw a probability tree, you didn't have to actually solve the numbers of the probability tree, but you can use the image of a probability tree to help you calculate the number without actually going along the tree. Okay, so well done if you got that. Let's have a look at the next topic now. Venn diagrams. So if you haven't done this question yet, give it a go. And if you have done it, let's jump right in. So we got our Venn diagram now, okay? So at a college, a total of 28 students, very important bit of information that, 28 students, study 1 or more of science subjects, biology, chemistry, and physics. The 28 students form the universal set. Remember, that's Z, which just means it's literally the box. It's everything in the box is the universal set. Some parts of the Venn diagram below have already been completed. It is also known that 5 students study only biology and 13 students study chemistry. So here we go, complete the Venn diagram. Okay, so let's use this information. 5 students study only biology. So the segment that represents only biology is this section here, because there's no overlap with physics or chemistry. They only study biology. So we can plop in a number 5 in there. The next question is 13 students study chemistry. So in this box here, I'm going to write just under the chemistry in a bracket, so it's not outside the box. I'm going to put 13. So I know 13 people study chemistry. And the chemistry circle is this one. So all the numbers in this circle should add up to 13. Currently, we've got 6, 2, and 1, which is 9. 9 plus something is 13, and that is 4. We've only got one place we can put that. So we can chuck 4 in there. Now the final one, how many people only study physics? Well, wait till the start. There are 28 students in total. So you have to add up all the numbers in here. So 5 and 2 and 3 is 10. 6 and 4 is also 10. So we've got 20 plus 1, 21. In the rest of the space, we account for 21 people. Therefore, the difference between 21 and 28 is 7. And there was 0 people who didn't study either. Who didn't study any of them. So that's good as well. We're happy with that. Okay. How many students study biology and chemistry, but not physics? We're looking for the overlap of biology and chemistry. Okay, so here we go. You would have hopefully recognized that this is the overlap. Ta-da. And then all you do is add the numbers up. 2 plus 6 equals 8 people. Easy peasy, all right? And then part C. One of the students is chosen at random. What is the probability that they study biology? So let's highlight the biology circle first of all. So one of the students chosen at random, probability that they study biology. Well, this is our biology circle, okay? So all the numbers in this will tell us how many people study biology in total. And if you add them up, we have got 5 plus 2 plus 3 is 10 plus 6 is 16. So 16 pupils study biology out of 28. Out of 28, because that's the pupils there were in total. Turn that into a fraction, 16 over 28. You can simplify that to 4 over 7. And as a decimal, that is 0.5722 decimal places. Okay, job done. So well done if you got those right. And let's have a look at the last question of the module now. Interpreting histograms. So if you haven't tried the question yet, pause the video and have a quick go. And if you have done it, let's jump right in. So histograms. This histogram in particular is showing the distribution of the heights of a group of 50 children. And we've got the diagram here. Now remember, with histograms, the number of people or the number of things, in this case we're talking about people, the number of people is equal to the base times the height of the bars in the histogram, okay? But the most important part is you need to actually make sure you're reading the scales properly, because if you assumed all of these were 1, 2, 10s or whatever, then you'd get it wrong. You need to actually read off the scales, okay? Read off the X and the Y axis. So the group visits a theme park. One of the rides has a minimum height restriction of 1.2 meters. What percentage of children will be able to go on the ride? So which of these bars represent a height greater than 1.2 meters? Well, we've got one here and we've got one there. So let's call this the 120 to 125 height range. And then let's call this one the 125 to 140 height range, okay? So how are we going to figure out the number of people in 120 who are between 120 and 125 centimeters high? Well, use this. The number of people is the base times the height. So the base of this rectangle is, well, 120 to 5. It's a base of 5. And its height of, read the y-axis, it is a height of 2. 5 times 2 equals 10 people. So there's 10 people who have a height between 120 and 125. Now for the people who have a height between 125 and 140, it's the base, which is 125, 140, is the base is 15. And the height, read off the y-axis, is 0.6. Get your calculators out. 15 times 0.6 is 9 people. Add them up. 10 plus 9 equals 19. So 19 people over 120 centimeters. Okay, but the question is, what percentage of children will be able to go on the ride? So to find a percentage, it's just this 19 divided by the total number of children, which is 50. 19 divided by 50, get your calculators out, unless you know this off the top of your head, and you should get 0.38, which as a percentage is 38%. 38% can go on the ride. Okay, let's have a look at the next question now. So, creating histograms. So this table summarizes the amount of money collected by 100 boys in a sponsored charity event. Okay, and we've got the table here. And then we're asked to draw a histogram to represent this distribution. Okay, so pause the video and have a go at this question. If you've already had a go, let's go through the answers. So just to remind ourselves, if we look back at the last question now, we can see that the bars in this histogram are all different heights and widths, okay? But the overarching rule with histograms is that to find the frequency or the number of people represented by a bar, all you have to do is multiply the base times the height. Okay? And that's what density histograms, that's how they work. But the difference with these ones is if you look at the axis, they tend to be very different from normal graphs. Normally the x and y are very similar numbers, sort of. In this case, we've got extremely different numbers. We've only got 1, 2, 3 on the y-axis, and we start at 100 and finish at 140 on the x-axis. So that's something to bear in mind when working with histograms, okay? So for this question, if we look at the first part now, we know that the amount is 0 to £10, and we know that the frequency was 5. Okay, so let's just think about this. So if we remember the formula, we've got the base times height equals the frequency, okay? So if we just make a little table out of this. So if you just remember at the top, that's the numbers we're using. The base times the height equals the frequency. In this case, the base is the amount of money, okay? And the height is the frequency density. That's how far we go up the y-axis, okay? So let's just call this frequency density, okay? So for the first question, if it's 0 to £10, that means we've got a base of 10, okay? And we're told the frequency is 5. So therefore, 10 times something is equal to 5. So you can reverse engineer this. If 10 times something is equal to 5, that means 5 divided by 10 is equal to our missing number, and 5 divided by 10 is 0.5. Therefore, the height for the first bar is going to be 0.5. So we've got a base of 10, so take care with the units. So we've got 1, 2, 3, 4. So we're going to go 5 squares across because each square is worth 5. And the height is going to be 0.5. So take your time, find 0.5 on the y-axis, join it up, and there's your first bar. And if you reversed engineered this, remember to calculate the frequency using a histogram, you multiply the base times the height to get the frequency. So 10 times 0.5 is 5. So that first one's correct, okay? Second one, again, the amount is 10 to £20. So that base is also going to be 10 units across, okay? Because 20 take away 10 is 10. So now 10 times something is going to be equal to 12. Okay, again, we can rearrange the formula slightly. So 12 divided by 10 is equal to 1.2. This is going to be our height for our second bar in this histogram. So we've got a base of 10, so that goes to 20, and we've got a height of 1.2. So look at the y-axis, be careful, because it's not always the same between graphs. So we've got 1.2 there, draw it down, and boom. So this is our second histogram bar. And just to reverse engineer it, if you think about it, 10 times something is 12, 10 times 1.2 is indeed 12. So this is a correct bar for our histogram, okay? Let's do the third one now, 20 to 50. So the base for that one is going to be 30, because 30 take away 20 is, 50 take away 20, sorry, is 30. 30 times something is equal to 48. Again, we can just re-engineer this, we can rearrange it. So 48 divided by 30 equal to 1.6. Therefore, the missing number is 1.6. So we need a base of 30 and a height of 1.6. So it's from 20 to 1, 2, 3, 4, 5. Always double check when you're counting. And then the height was 1.6, which is all the way up here. Take it across 30 units, bring it down, and bring this bar down. And this is our third histogram. I'm going to draw lines going a different direction. Try to overlap them, just so you can see these are all different bars. Okay. Again, to double check it, 30 times 1.6 is indeed 48, which was our frequency we're trying to get to, okay? Next one, we've got 50 to 80. Again, that's going to be a base of 30 because 80 take away 50 is 30. 30 times something equals 27. Rearrange it just to double check. 27 divided by 30 is equal to 0.9. Therefore, we're looking for another rectangle with a base of 30 and a height of 39. 50 to 80. That's our 30 wide. I'm going to go 0.9 up. Take care with the scale to there. Bring it down. Job done. And I'm going to do polka dots for this one. How about that? Just to double check your answer, just think to yourself, or use a calculator to double check it. Is 30 times 0.9 27? Hopefully your calculator should agree with you. So we're happy with this bar now. Last one. 80 to 100, well, that represents a base of 20, multiplied by something is equal to 8. Once again, rearrange it. 8 divided by 20 is equal to 0.4. Therefore, 20 times 0.4 is equal to 8. So the width is going to take us to the end of the graph. Take it to 0.4, draw it across. And what haven't we done now? Oh, let's do crosshatched for the last one. Okay, so 20 times 0.4 is indeed 8. Okay, and there you go. That's your histogram. That's a frequency density histogram. Okay, and if you times the base times the height of all of those bars, you would get the frequencies given in the table. Okay, let's have a look at the next question now. So sampling. So there's 3 types of sampling. We had systematic, random, and stratified. Okay, so let's go through the first one, which is systematic. So there's a queue of 96 people waiting to buy concert tickets. Liam has 8 vouchers to hand out, offering 20% off ticket prices. He's decided to use a systematic sampling method to select who receives the 8 vouchers. Liam has randomly selected the 6th person in the queue to receive the first voucher. Use the table below to give the positions in the queue of the 8 people who would receive the vouchers. Okay, so systematic sampling is that we are looking to pick every nth person. Okay, so we are trying to find this number here. We need to pick every nth person. Okay, so pause the video and have a go. If you've already had a go of it, let's go through the answer. So like we said, we're looking to pick every something person. Okay, so either every 5th person, every 10th person, every 50th person. Okay, and the formula for this was population divided by sample size. And that would give us our interval. That would give us our sample interval, okay? So the population in this case is 96. The sample size was 8. Therefore, the sample interval was 12. Therefore, we're looking to pick every 12th person, okay? And then all we do, we take every 12th person, we apply it to this table here, okay? So we start picking the 6th. If we then pick a person 12 numbers later, that would give us the 18th person. Another 12 numbers later would be the 30th. Another 12 numbers would be 42nd. Hello. '42nd, 54th, and so on, so forth. Okay, so you just keep adding 12 to all the numbers until you run out of numbers. Okay, so 90th to finish off with. Okay, so double check you're adding 12 every time there. And there you go. That would be a systematic sample where we've picked every 12th person and we were given our first position in the question. That's every 6th person. Okay, Oh, the first person was the 6th person, okay? Let's have a look at the next topic. Random sampling. So in the lesson, we talked about a few various ways of getting a random sample, but this question is actually looking to get us to use a random number table, okay? So our hospital decides to take a random sample of its 120 doctors to select those needed for the survey. Use the following list of random numbers to select the first 5 doctors. You must start with the first number in the list, explaining clearly how you are using the numbers to select the sample. Okay, so first of all, let's think about how we're going to use this before we write down a method, okay? So we need to pick, we need a random sample of 5 doctors, and there are 120 in total, okay? So 120 is a 3-digit number. These random numbers here are also 3-digit numbers. 032, we could pretend that is 32. 520, we could pretend that is 520, and so on and so forth, okay? So first of all, let's number our doctors 1 to 120. So number doctors 1 to 120. Okay. Then we're going to look at the 3-digit random numbers. And we are going to include the first 5 between 1 and 120, okay? So let's go through this. Let's have a think about this in practice, okay? So 120 is a 3-digit number, and we've been given random numbers that are 3 digits, okay? So the first one here is 032. So that means we've got 032. That means we're going to pick the 32nd doctor. So we've got 32nd one, job done. Now, 520, that's bigger than 120, so we can't have that in our random sample. The next one, 021, well, that means we're going to pick the 21st doctor in the list, okay? Job done. We can't have 924 because it's higher than 120. Can't have 152 because it's higher than 120. And you would just go through the list until you reach numbers that are between 1 and 120. So we've got 081 here, so 081, that means we're going to pick the 81st doctor as well. He's going to be one of our 5. Keep getting rid of them until we get to, keep going. Now, we've got 032 again, but we can't include 032 again because if we think about it, we've already picked the 32nd doctor. Now we've got a duplicate. So we can't include this second 032, okay? So if you want, you can add that to your, so let's include that to our method actually. So we're going to remove, not including duplicates, okay? It's a good thing to add to our method, okay? So we're not going to have 032, just keep going through it. We've got 055. So that's going to be the 55th doctor, and then keep going until we get to 105. So that's going to be the 105th doctor, okay? So then the final point of our bullet point is we will we'll start from the lowest number. That makes sense. We're going to have to pick the 21st, 32nd, 55th, 81st, and 105th doctor. Let's draw that and a bit better. And 105th doctors. Okay, and we stop there because we only wanted 5 doctors. We've got our 5 doctors, so that is our random sample of 5 doctors using a random number table. Okay, so let's have a look at the last question now. Okay, so stratified sampling. So the table shows number of year 11s attending schools in Cumulative. In total, there are 690 year 11 pupils attending the 3 schools. A new youth centre has been set up in Cumulative. On the opening night, a total of 80 year 11 pupils from these 3 schools are going to be invited to attend. Using stratified sampling, using the stratified sampling method to calculate the number of year 11 pupils from each school who should attend. You must show all your work in. Okay, so pause the video, have a go at this question. If you've already had a go, let's go through it. So just to remind ourselves, the formula for stratified sampling is strata, so strata size, divided by population, multiplied by sample size, okay? Sample size. Now, people sometimes forget which one goes on top, whether it's strata size or population size. Remember, this needs to be a number that is less than 1, okay? So the smaller number needs to go on top, because when we divide them, we want a smaller number. So when we multiply it by the sample size, we get a proportion of that sample size, okay? So the smallest number goes on the top, which should always be the strata size, okay? So this is our information. Now let's have a look at these questions now. So for Cumulative, let's think about what we need. We need strata size, we need the strata size, we need the population, and we need the sample size, okay? Now for a lot of these, this is all going to be the same information, okay? The only thing that's going to be different is the strata sizes, okay? So the strata for Cumulative is going to be 307 because there's 307 pupils in Cumulative. For Cumulative High, it's going to be 239. So there's 239 pupils in Cumulative. And in Henclwyd, the strata size will be 144 because there's 144 pupils, year 11s in Henclwyd. Population, this is going to be the same for all of them because we're looking for a population. Our population is all the year 11s in all these schools. So population for all of them will be 690. And the sample size for all of them will all be the same because we're looking for a total of 80 pupils of these year 11s in all these different schools. The sample size will be 80 for all of them, okay? So let's think about, so the first one, let's do half, H-A-F. Okay, so we're just going to use this formula, and this will give us our strata sample size. Sample size. Okay, so for Cumulative, I'm just going to use half here. So strata size is 307 divided by the population, which is 690, multiplied by the sample size, which is 80. And if you type those into a calculator, you should get 307 divided by 690 equals, double check that, 307. You should get 35.59. Okay, so that's the 2 decimal places. But remember, we can't have 35.9 of a person. It has to be 36. Okay, we have to round to nearest whole number. So we're going to take this up to 36, and this is the nearest integer, nearest whole number. Okay, so that's Cumulative. 36 pupils from Cumulative. So 36 year 11s. What about Cumulative High? So I'm just going to call this high. So high. Again, what's our strata? The strata is 239. Just going to reuse that formula. 239 divided by 690 multiplied by 80 is equal to, chuck it in your calculator, and you should get 27.71. This is to 2 decimal places. We don't like that, so we're going to round it to 1 decimal place, which will be, sorry, not 1 decimal place, to the nearest whole number, which is 28 year 11s from Cumulative High. Again, this is to the nearest integer. And then the last one, we've got Henclwyd. Okay, let's put that wrong. Henclwyd. Okay, so same formula, use the formula again. So strata size is 144 divided by the population, 690, multiply that by the sample size, which is 80. So 144 divided by 690 times by 80, that gives us 16.69. 0.70 to 2 decimal places. Okay, 16.7 to 2 decimal places, but we can't have it to that. It's round to the nearest whole number, so we have got 17. Nearest integer. Okay, so these are our numbers. Just to double check, we are looking to make sure that these numbers add up to 80. Okay, so hopefully we want these numbers to add up to 80. Okay, so 36 plus 28 plus 17. If you add them up now, you should probably, even without adding them, you should notice that this will not add up to 80 because we've got two evens and an odd number in there. So something is going to be slightly askew. So we've got 81. Okay, so this is one too many. Okay, so this is one too many. So we need to take away one from one of these because we have one too many. And if you think about this, we rounded all of these up. 35.59, we rounded that up. 27.71, we rounded that up. 16.70, we rounded that up. So we need to take one away. We need to take one away from the most rounded number, okay? From the most rounded number. And the most rounded one in this case is, oops, change that to yellow, is this one, because we've added 0.41, whereas the rest of them we've added 0.3. So we're going to decrease 36. So we're going to decrease to 35. We're going to decrease to 35 because of rounding. Because of rounding. Okay, so we're going to use 35 instead. So let's get rid of that. So we're going to do 35 plus 28 plus 17. And if we add all those up, we should get 80. Okay, so these are the numbers we want. And just